Welcome, everyone, to today's AI on AI podcast, where we dive deep into cutting-edge innovations with a mix of technical insights and real-world business savvy. Today, we're unpacking bitnet b1.58 2b4t, the first native 1-bit LLM at the 2 billion parameter scale. So buckle up.
Thanks for having us. It's truly fascinating how bitnet b1.58 2b4t leverages native 1-bit quantization, shaving down memory footprints and energy consumption while still delivering competitive results. It's like turning a diesel engine into a turbocharged electric motor without sacrificing performance.
Absolutely, Expert 1. And what really jumps out is the custom bit linear layers. They replace full precision linear layers with ones that quantize weights to 1.58 bits, using an absolute mean, abs mean quantization strategy, mapping them to ternary values of -1, 0, and +1. It's a bold move that shows how aggressive quantization doesn't necessarily mean a drop in performance.
I completely agree. The idea is reminiscent of the Pareto principle. You get 80% of the performance with only 20% of the resource usage. A true efficiency-performance trade-off that many older models just can't manage.
And let's not forget the GPU inference side. Custom CUDA kernels were developed to pack 4 ternary values into a single int8 and then unpack them on the fly within shared memory. It's a technical deep dive that's a game changer for high-speed inference under resource constraints.
From a business perspective, this is huge, right? Imagine a retail company deploying these models on edge devices in stores, cutting operational costs significantly by reducing energy consumption and memory usage, which, as a rule of thumb, can cut costs by at least 15% annually.
Wow, that's a striking analogy. It's like swapping a gas guzzler for an ultra-efficient hybrid. Expert 2, could you elaborate a bit on how this 1-bit quantization compares to traditional post-training quantization methods?
Sure thing. The standard PTQ methods like INT4 quantization with GPTQ or AWQ typically degrade performance relative to the full precision baseline. However, bitnet's native 1-bit training from scratch avoids those pitfalls, maintaining competitive performance metrics even compared to post-trained models.
And what's really intriguing is how the training process itself was structured, starting with a high learning rate, cosine schedule, and then a cooldown phase at a lower rate with no weight decay. That kind of two-stage approach ensures stability in training, particularly for a model that's operating with such low bit precision.
Exactly. Plus, they incorporated sub-LN normalization in the bit linear layers, which is critical for training stability when dealing with quantized activations. It's a nuance that might be easily overlooked, but makes a significant difference in maintaining high accuracy across language tasks.
Let's not overlook the business implications here. The energy savings per arithmetic operation are phenomenal, with numbers showing that INT8 consumes nearly 10 times less energy than FP16 in multiplication operations. Companies can save not only in hardware costs, but also in operational cooling and power consumption.
Yes, and speaking of real-world examples, I read about a case where a financial services firm deployed optimized LLM inference on commodity servers, reducing their operational latency and running costs dramatically. This model's low memory footprint and energy profile could revolutionize similar deployments in other sectors like healthcare and logistics.
That's quite a compelling business case, indeed. Expert 2, you mentioned earlier about the GPU inference improvements. Can you provide a bit more technical detail about that custom CUDA kernel?
Sure, the kernel follows a pack store load unpack compute strategy. Essentially, it packs several ternary weights into a compact representation, loads them into the GPU's shared memory for high-speed access, then unpacks immediately before performing the efficient matrix multiplication with the 8-bit activations. This minimizes memory bandwidth usage and exploits GPU parallelism beautifully.
It's like having a secret backstage pass for the GPU, cutting down instruction overhead and allowing computation to happen nearly as fast as the hardware permits.
And this is where the potential for hardware co-design comes in. We might see future GPUs or specialized NPUs that are designed specifically to handle these low-bit arithmetic operations natively, further accelerating the benefits observed today.
On the flip side, I have a contrarian view. While everyone's focused on efficiency, I think we might be missing the real bottleneck in deployment. The custom low-level optimizations demand significant engineering effort, which companies may not be ready to invest in unless they see a rapid ROI.
True, but if you look at cost-benefit analyses, once you've optimized the kernel for a given hardware setup, the long-term savings in energy and infrastructure can outweigh the initial development investment. It's like the 80-20 rule in action. Small upfront costs yield large operational benefits.
I love that interplay between technical nuance and business strategy. It's exactly what makes discussions like these so rich. Expert 3, could you talk about the training data and methodology?
Absolutely. The model was trained on a whopping 4 trillion tokens, mixing general web crawls with curated texts and even synthetic mathematical data. The idea is to capture a diverse range of linguistic structures and problem-solving scenarios, ensuring that the model is robust in reasoning as well as language understanding.
And the use of supervised fine-tuning with diverse conversational datasets like WildChat and Wizard LM Evel-Instruct shows the emphasis on aligning model outputs with human preferences. They even incorporate direct preference optimization, which bypasses the need for a separate reward model, streamlining the overall process.
That DPO phase, running for 2 epochs with a carefully tuned learning rate, is a perfect example of how modern training regimes are evolving, moving beyond classical RLHF to methods that are more efficient and directly aligned with desired behavioral outcomes. Plus, the model's architecture cleverly removes all bias terms from the linear and normalization layers, similar to Llama's approach, which simplifies quantization and reduces the parameter count. It's an elegant design choice that contributes to both performance and efficiency.
From the business lens, this streamlined architecture means easier deployment, lower compute requirements, and less dependency on high-end hardware, opening the door for startups and smaller companies to leverage advanced AI without the typical infrastructure overhead.
Incredible insights. And it makes me think of a famous quote by Einstein: "Imagination is more important than knowledge." Here, imagination in model design is clearly paying off for both technical and business fronts.
That's a great point, host. Innovative design choices, like native 1-bit training, challenge conventional wisdom and invite us to rethink what's truly necessary for state-of-the-art performance.
And it's not just academic. Real-world deployments confirm that these innovations translate into practical benefits. For instance, companies in the IoT space could harness such low-footprint models on edge devices, ensuring real-time responsiveness while drastically cutting energy bills.
I'd add that the modular nature of the code, the public release via Hugging Face, and the bitnet.cpp library for CPU inference shows an open-source commitment that accelerates community adoption and iterative improvement across both research and industry.
Absolutely. And that community-driven approach often leads to unexpected improvements and adaptations. It's like open-source, crowdsourced innovation, where every tweak can have outsized effects in performance and usability.
Yes, and one can't help but appreciate the potential of extending this model to multilingual tasks and even integrating multimodal capabilities. Imagine an efficient model that handles both text and images in remote environments with minimal power consumption.
That's a fascinating vision, an AI that could operate efficiently in, say, disaster zones or remote research outposts. Expert 2, any final technical thoughts?
Just one more nuance to appreciate: the balance between aggressive quantization and the careful tuning of training schedules, including the 2-stage learning rate and weight decay approach, demonstrates that even radical changes in data representation require a holistic, well-calibrated training strategy to work effectively.
And that balance, in essence, is the art of this innovation, ensuring that reducing precision doesn't equate to sacrificing capability.
I concur. It's a delicate dance between efficiency and accuracy, one that bitnet b1.58 2b4t seems to have choreographed beautifully.
And with hardware evolving, we might soon see even more dramatic transformations where these techniques become not just optional tweaks, but foundational standards in AI model design.
In turn, businesses will have access to more scalable, sustainable, and cost-effective AI solutions, driving a fundamental shift in how AI is deployed across industries.
What an electrifying conversation this has been. A true blend of deep technical dive and strategic foresight. Thanks to all our experts for sharing such rich insights.
It's been a pleasure. Always exciting to explore how innovation can redefine both technology and business landscapes.
I'm thrilled we could unpack these nuances together. It's like rebuilding an engine while driving the car, but with impressive results.
And it's these kinds of discussions that remind us how interdisciplinary collaboration fuels progress, both scientifically and commercially.
Exactly. And let's not forget to keep a sense of humor amidst all this complexity. I'd say we managed not to get too bit by the low-bit puns today.
Well, if that wasn't the icing on the cake, it certainly shows that sometimes a little laugh is all you need to appreciate serious advances.
Thanks once again, everyone, for this insightful and lively debate. Stay tuned for our next episode as we continue exploring innovations that power the future of AI. Welcome back, everyone, to part 2 of our deep dive, where we're going to get even more technical about the implementation nuances of bitnet b1.58 2b4t and explore its robust business applications.
Let's jump right in. On the implementation side, one key innovation is the custom CUDA kernel that's engineered for the w1.58A8 matrix multiplication, which, as you recall, packs multiple ternary weight values into an int8 format. This packing process is crucial to achieve low memory bandwidth and maximize speed.
Exactly. Expert 1. The kernel employs a pack, store, load, unpack compute sequence that minimizes data movement between HBM and GPU shared memory. And what's remarkable is that this strategy leverages the GPU's inherent parallelism, effectively reducing latency by nearly 50% when compared to naive implementations.
And from a business perspective, that kind of efficiency opens up a new era for edge computing. Think about logistics companies deploying real-time analytics at distribution centers without investing in costly, high-energy GPU clusters. It's a transformative cost saver.
Diving deeper into the technical details, the kernel's optimization isn't just about packing bits. It also involves the clever use of bit-level arithmetic operations, which, when coupled with optimally tuned 8-bit activation quantization, ensures that there's barely any performance loss, even with such low-bit precision.
Absolutely. And consider industries like retail, where real-time personalization is key. This technology can enable smart kiosks and digital signage that respond instantaneously to customer interactions, all while operating on minimal power, which is a serious competitive advantage.
It's like engineering a precision Swiss watch inside a smartphone, compact, efficient, and incredibly reliable. Expert 2, could you expand on how the learning rate schedule and weight decay strategy play into this robust implementation?
Sure. The training protocol employs a 2-stage learning rate schedule, where an aggressive high-rate phase is followed by a cool-down period with no weight decay, allowing the model to fine-tune its representations. This approach not only stabilizes training, but also inherently supports the quantization process, ensuring that weights represented in 1.58 bits remain robust.
And to add a bit more on the technical side, the removal of bias in every linear and normalization layer simplifies the arithmetic operations required during both training and inference, a design choice that, while subtle, has a big impact on the overall efficiency of the model.
On the business application front, this streamlined design means that companies can deploy these models on existing, lower-end CPU systems using the bitnet.cpp library, which results in both reduced hardware investment and lower operational energy consumption. A win-win situation for many sectors.
Building on that, the implementation on CPUs is just as impressive. The bitnet.cpp engine is fully optimized for standard multi-threaded environments. So even in resource-constrained deployments like remote IoT sensors, the model can deliver fast, lossless inference without the need for specialized accelerators.
I've seen a case study in a smart city project where local government agencies used similar low-footprint models to monitor traffic and public safety in real time. The savings in energy and maintenance costs made widespread deployment both feasible and sustainable.
It's striking how the intersection of hardware optimization and algorithmic innovation creates such a broad spectrum of applications, from high-end GPU clusters to everyday CPU-based systems.
Right. And don't forget that the mixed precision computations, where we combine 1.58-bit weights with 8-bit activations, are fine-tuned to exploit the inherent sparsity in data, reminiscent of the 80-20 rule, where a minor loss in precision yields major computational gains.
And that's where the aha moment lies. Engineers are turning what once was considered a compromise into a deliberate strategy to redefine efficiency, a paradigm shift especially relevant in today's cost-sensitive market.
From a strategic standpoint, companies that adopt such models can reallocate their saved energy and compute resources towards innovation, effectively reinvesting in R&D and accelerating digital transformation initiatives, a clear business multiplier.
Let me throw in an unexpected insight here. While many focus solely on performance metrics, the true bottleneck for many enterprises isn't accuracy at this point, but rather scalability and deployment speed. These low-bit models address that head-on by drastically reducing latency and power usage.
Exactly. And in sectors like healthcare, where every millisecond counts in patient diagnostics, the ability to run high-caliber models on low-power devices can be the difference between timely intervention and a missed opportunity.
That's a fascinating twist, turning efficiency into a direct business enabler. Expert 2, any further thoughts on the kernel's role in future hardware co-design?
I believe this is just the beginning. Future GPU and even NPU architectures could incorporate dedicated support for low-bit computation natively, which would not only further slash energy consumption, but also enable these models to scale even more dynamically in real-world applications.
And it's not just about the hardware. The software ecosystem is evolving too, with frameworks like the Ladder framework and enhanced Python libraries that streamline the integration of these custom kernels into existing AI pipelines.
For business leaders, this evolution translates into reduced total cost of ownership for AI systems, improved sustainability metrics, and faster time to market for AI-powered products and services, a potent mix in today's competitive landscape.
Let's also not skirt around the challenges. A major hurdle remains the need for deep technical expertise to fine-tune these models for specific deployments, which means ongoing collaboration between hardware engineers, software developers, and business strategists is essential.
And that interdisciplinary dialogue is exactly what companies like agile startups and forward-thinking multinational firms are embracing, recognizing that blending technical prowess with strategic business insights is the surest path to innovation.
Well said, Expert 5. It's like assembling a perfect orchestra where each section must perform in harmony for the overall masterpiece to shine.
And on that note, while we celebrate the technical triumphs of bitnet b1.58 2b4t, it's clear that its real impact will be determined by how effectively businesses can translate these efficiencies into tangible outcomes in the field.
Absolutely. It's an exciting time to witness the convergence of deep technical innovation and strategic business application, redefining what's possible in AI deployment, both at scale and in everyday contexts.
And as these models mature and the ecosystem evolves, we're likely to see a gradual shift where low-power, high-efficiency AI becomes the default for a wide range of industries, from autonomous vehicles to mobile health monitoring devices.
I, for one, am excited to see future developments where not only energy and latency are optimized, but where these innovations drive entirely new business models, perhaps lowering entry barriers for small enterprises and fostering a more competitive global market.
Ultimately, businesses that leverage these innovations are poised to lead in sustainability, cost efficiency, and customer responsiveness, transforming sectors by turning technical ingenuity into strategic advantage.
What an incredibly rich discussion. Thank you all for this deep dive that so brilliantly marries technical details with real-world business insights. We're truly on the cusp of a new frontier in AI.
It's been a pleasure sharing these insights. Here's to a future where efficiency and innovation fuel unprecedented growth and transformation.
As we wind down today's conversation, let's recap. We've seen how bitnet b1.58 2b4t redefines efficiency through its custom CUDA kernels, strategic learning rate schedules, and advanced quantization methods, all of which have profound implications for both technical performance and business cost savings.
Absolutely. The shift to a native 1-bit training paradigm at the 2B parameter scale isn't just a technical upgrade. It's a paradigm shift that blends precision with efficiency, proving that less can truly be more.
And our deep dive into the pack store load unpack compute sequence highlights how these innovations reduce latency and energy consumption, setting a new standard for sustainable AI deployments that scale from edge devices to enterprise data centers.
From a business perspective, the ability to deploy such models on both high-end GPUs and standard CPUs means industries, from retail to healthcare, can dramatically lower operational costs while accelerating time to market for critical applications.
What's especially exciting is how these technical breakthroughs foster interdisciplinary collaboration. Overcoming challenges in low-bit computation requires a seamless integration of hardware optimizations, software innovations, and strategic business insights.
And don't forget the real-world impact. Case studies in smart cities and retail have already shown that leveraging these low-footprint models can deliver tangible energy savings and enhance customer experiences, unlocking new avenues for competitive advantage.
In summary, today's discussion has taken us through the nuanced innovations of bitnet b1.58 2b4t, revealed its potent technical mechanisms, and mapped its significant strategic business applications, illustrating a future where efficiency and performance coalesce to fuel next-generation AI.
It's been an enlightening session, symbolizing an orchestra where every technical refinement plays its part in composing a masterpiece that's both innovative and strategically sound.
And as Einstein once said, imagination is more important than knowledge. Today, that imagination has translated into concrete steps toward transforming AI for sustainable, wide-scale use.
Thank you all for joining us on this journey of discovery. We hope you're as excited as we are about the future of efficient, high-performing AI. Stay tuned, keep innovating, and see you next time.